Welcome to H2O, the A to Z of chemistry. I'm Dr. Ritu Johar, your educator for this course on chemical bonding, and I hope you are enjoying this course with me. Today we are going to begin with lecture 39 from the course, but make sure you watch the previous ones before viewing this one. In the last lecture, we started with a discussion on back bonding with the help of one example, and the example was the Bf3 molecule. But is it only Bf3 molecule that shows back bonding? No, not at all. There are going to be so many examples in chemistry where there is going to be back bonding. So today we are going to begin with back bonding part 2, and there's going to be a back bonding part 3 also, because we have so many examples of back bonding, and well, there are going to be so many applications of back bonding as well. Now what do I mean by these applications? Well, in the last lecture, while you were discussing the example of BF3, you also learned that various boron trihalides, the Lewis acid character of them, this is based upon the strength of the back bonding in them. So this is one application of the back bonding concept. There are going to be so many more that you have to learn. For example, let me give you one more. We have NH3 and we have NF3 molecules. Out of these two, what we find is that the NF3 molecule, this is having a smaller bond angle than the NH3 molecule, and this is something that you have learned in the previous lectures. But now if I tell you that the PF3 molecule, this has a larger bond angle than the PH3 molecule rather than being smaller, well, how are we going to explain it? Well, this is going to be one application of back bonding. So you have a lot to learn, and all these things that you're going to learn in this lecture, well, this is going to be very important for your examinations. If you want to excel your JEE mains, NEET, and especially JEE advanced, well, this is going to be a one watch lecture. You should not miss it. All right, so let us begin the learning. I hope you are going to enjoy it. So quickly revising back the concepts that we learned in the last lecture, back bonding is the phenomenon involving the transfer of a lone pair from the fully filled shell of one atom to the unfilled shell of the adjacent bonded atom. This is very important that the two atoms, they should be bonded to one another. There is going to be first a sigma bond formation between them, and after that this lone pair transfer from one atom to the unfilled shell of the other is going to happen. So this is going to be possible between atoms in a compound in which one atom has a lone pair of electrons and the other has a vacant orbital placed adjacent to each other, and this is a kind of pi bonding. It can be a partial pi bond, it can be a full pi bond. This depends upon the relative donating and the accepting capability of the donor and the acceptor atoms. And consequently, the bonding, this is going to acquire a partial double bond character because of the pi bond that is being formed. Generally, in the back bonding, this increases the stability because this is going to help complete the octet of the molecule. This can also be visualized as a type of resonance. This you have seen in the case of the Bf3 molecule that we studied in the last lecture. There are going to be many examples coming up now further. Generally, the donor atoms, they are the second period elements carrying the lone pair like fluorine, oxygen, nitrogen and carbon, and there can sometimes be chlorine, bromine, iodine, phosphorus, sulfur also acting as donor atoms under suitable conditions. So this is how we are going to make these two lectures also. We will be first of all discussing in this lecture when fluorine and oxygen act as the donor atom, and in the next lecture we will be seeing the examples and the applications where the nitrogen, carbon and the other atoms, they are acting as the donor atoms. So please do remember that back bonding, this is called as a pi coordinate bonding. Why a pi coordinate bonding? First of all, why a pi bond? Because the first bond between the two atoms is a sigma bond, and then the back bond is the bond which is the second bond that is formed, so it is a pi bond. And it is a coordinate bond because both of the atoms, they are not contributing one electron each for the bond formation. Only one of the atoms is contributing the electron pair. So it is going to be a coordinate bond and which is going to be pi bond in nature. Now the compounds, they can be of two types when they are going to show back bonding. First type of compounds are going to be those in which the side atom is going to donate the electron pair to the central atom. For example, in the case of the Bf3 molecule that we have studied in the last lecture, it is fluorine, which is a side atom which contributes the electron pair for the formation of the back bond. And then we have the compounds in which the central atom donates the electron pair to the side sources. For example, in the case of Tri Methyl Amine, here nitrogen, the central atom, will be donating the electron pair. We are going to study all of these examples in detail. So the next we have is what you have to remember, the conditions necessary for back bonding. The first condition, that any one atom in the pair, they should have at least one lone pair of electron and the other should have an empty orbital. And the second is that at least one atom should be a second period element and the other, this can belong to the second period or the third period. This is what you are going to see generally, although there are going to be some exceptions also. Now, what are the effects of this back bonding? First effect, you've already learned that it can increase the stability of the molecule by completing the octet. But apart from that, what are the effects of back bonding? Well, back bonding, this results in a decrease in the bond length and increase in bond order because of the partial double bond character. Then it does affect properties of the molecules like hybridization and dipole moment. The bond angle of the molecule may or may not increase, but it never decreases. Just remember this is very important, that the bond angle may or may not increase because of back bonding, but it is never going to decrease. Giving you one example of the effects of back bonding before we even begin the complete discussion. We have carbon monoxide molecule, a very important molecule which exhibits back bonding. Okay, so what happens over here in carbon monoxide? Carbon monoxide is made up of carbon and oxygen. Oxygen is more electronegative than carbon. So there should be an electron pair shift more towards oxygen and hence there should be an appreciable value of the dipole moment of the carbon monoxide bond. But what we see is that the dipole moment value, which is 0.11 dpi, this is much less than the expected value because of the back bonding from the lone pair of oxygen into the vacant orbital of carbon. Right? So these is just one example. You are going to see so many examples and applications of back bonding in this lecture. So are you ready for some examples of back bonding and its applications? Well, they are going to be very important for you, and the first one that we will be learning is back bonding with fluorine as the donor atom. And then we will be discussing back bonding with oxygen as the donor atom in today's lecture, and the rest we will be continuing in the next lecture. So when we discuss back bonding with fluorine as the donor atom, the first molecule that comes into the mind is Bf3, because this is with what we had learned back bonding in the last lecture. So here we will be just quickly revising it because I have lot many applications of back bonding in Bf3 to be discussed with you today. So in Bf3 we have 3 bonds between 1 boron and 3 fluorine atoms, and this is going to happen when boron is going to be in its excited state. In its excited state it is going to be having 3 half-filled orbitals which will be undergoing sp2 hybridization, and then they will be participating in bond formation with 3 fluorine atoms, and as a result Bf3 this will be having a trigonal planar structure. All the 3 Bf bonds, they will be lying in one plane, and after that what will happen is that boron, this has one empty orbital, and fluorine, this has 2 lone pair filled orbitals with it which are oriented perpendicular to the internuclear axis. What this means is that at least one of these two and this one, they are going to become parallel to one another. And it is at this moment that fluorine can share its lone pair with the empty orbital of boron. Why does it need to share that lone pair? Well, it needs to share that lone pair because boron is still electron deficient after forming these 3 bonds. It has 6 electrons, and the moment this bond is going to be formed, well, the molecule is going to become stable because boron will also have its octet complete, right? So what do we have? The p orbitals of boron and fluorine, they become parallel to one another. Boron has empty p orbital and the p orbital of fluorine, this has a lone pair. Hence boron acts as the lowest acid and electron acceptor, and fluorine acts as a lowest base and electron donor. The fluorine donates its lone pair to boron and this bonding is called as back bonding. Now the type of back bonding between boron and fluorine, this will be called as 2p pi, 2p pi back bonding, because fluorine is donating its electron from the 2p orbital and boron is getting electrons in the 2p orbital, and a pi bond is formed between them. There is one bond between them already, which is the sigma bond, and the next bond formed is the pi bond. So it is 2p pi, 2p pi back bonding. And as a result of this, the bond between boron and fluorine, this is going to get a partial double bond character, but it can also be between this boron and fluorine and this boron and fluorine. So what this means is that, well, three resonating structures are possible. We see this to be a type of resonance that you can now understand, and hence this is going to be the resonance hybrid, where we will be having a partial double bond character on all of these three bonds. So next, let us discuss the effects of back bonding in BF3. Some of them we have discussed in the previous lecture, so we will quickly revise them, and then we will be seeing some more effects of back bonding in BF3. The first one is the bond length of the BF bond. So if it is a single bond, the value, this should have come to 1.5 Armstrong, but actually we find it to be 1.30 Armstrong, which is less than that of a single bond, but it is more than that of a double bond, which means it is going to be a partial double bond character. Similarly, what about the bond order? If it is a single bond, the value should have been 1, but actually it is 1.33, so it is a higher bond order. A higher bond order and a lesser bond length, what does that signify? A partial double bond character for the BF bond. Next, we have the bond enthalpy value comparison of the CF bond in CF4 and the BF bond in BF3. What is bond enthalpy? The amount of energy that is going to be released when 1 mole of bonds, they are formed. Okay, and it is going to be equivalent to the bond dissociation enthalpy value, which is going to be the amount of energy that is going to be required to break 1 mole of bonds. Alright, so what this means is that if we have the CF bond and we have the BF bond, boron is larger in size than carbon. You all know that in the period when we are going to move from left to right, what are we going to get? The size of the atoms that goes on decreasing. The other atom is similar, so what you will be having is boron to be larger in size, and hence the BF bond, this should be longer than the CF bond. If it is going to be longer, this means that it is going to be more easier to break, and if it is going to be more easier to break, the value of the bond enthalpy should be less than that of the CF bond. Okay, but what do we find? We find that in CF4, the CF bond enthalpy value, this is 515 kilojoule per mole, whereas in BF3 it is 646 kilojoule per mole. Why is it more? It is because the bond, this is stronger than a single bond. There is a partial double bond character. The bond length value is also going to be less, and it is going to be more difficult to break the bond, and hence the bond dissociation enthalpy value is going to be more, and conversely the bond enthalpy value, this is also going to be more. So I hope now you understand all these things which we have done in the previous lecture as well. So let us move on to some more applications. Next, let us discuss the effects of back bonding in all the boron trihalides. In fact, in all the boron trihalides, back bonding can take place. What is going to be the difference is the strength of back bonding. It is going to be the strongest in BF3, and it is going to gradually decrease and become the weakest in BI3. Why is it so? Well, because the strength of back bonding, this is going to be proportional to the size of the atoms participating in back bonding. What does that mean? What it means is, if we think about BF3. So BF3, which are the orbitals which are going to participate in back bonding? It is going to be a 2p of boron and a 2p of fluorine. Both of them 2p, so they are similar in sizes, and hence it is going to be a very effective overlap between the two because the orbitals, they are similar in size. When we move on to BCl3, it is going to be a 2p of boron and it is going to be a 3p of chlorine, which has become a bigger in size. Now the overlap is not going to be that effective, right? Because one of them is bigger in size. Similarly, as we move further from BCl3 to BBr3, it is going to be a 2p4p overlap, and if it is going to be a Bi3, it is going to be a 2p5p overlap. And because as the size of one of the atoms is increasing, well, the overlap is not going to be that effective, and hence we say that the best back bonding is going to take place in Bf3. This is going to be the strongest back bond that we have. Now the next question is, which of all these boron trihalides, which is going to be the best Lewis acid? You have to arrange all the boron trihalides according to the Lewis acid character. Now a molecule is going to be a better Lewis acid when it can accept an electron pair easily into the molecule. Right? Now, if we consider all these boron trihalides, if we consider first of all the bond between boron and fluorine. So here we have the shared pair moving first of all towards fluorine, because fluorine is the most electronegative, and as we move down the halogens, well, the electronegativity is decreasing, and hence we can say that for chlorine, the electron pair is going to be less towards chlorine, right? And as we move from chlorine to bromine, it is going to be still less pull towards bromine because the electronegativity is going to decrease further, and as we move towards iodine, similarly. So when we have boron and fluorine forming a bond, the electron pair is more towards fluorine, so boron is going to be more electron deficient. If it is going to be more electron deficient, well, it should accept an electron pair more easily in comparison to the rest of the boron trihalides. But that does not happen. The order is the reverse. Why is it the reverse? It is the reverse because of back bonding, right? So what we have as the order is the Bf3 is going to be the least lowest acidic, then BCl3, then BBr3, then Bi3. Why so? Because in Bf3 we will be having the maximum back bonding. So boron is no longer electron deficient. Fluorine has already given it an electron pair, shared an electron pair with it. So boron is the least electron deficient in Bf3 because of the best back bonding. And Bi3, this is going to have the least back bonding, so this is going to be the most electron deficient, and hence it is going to be the strongest lowest acid among all of these. Alright. Now the next we move on to the ease of hydrolysis of the trihalides of boron. What we find is that BBr3 is going to be maximum easily hydrolyzed, then BCl3, and the least is going to be Bf3. Again, I hope you can understand this is because of back bonding. Now what happens because of back bonding is that Bf3, this has a strong Bf bond. So when it is going to react with water, this is going to be the least easily broken bond, right? Compared to BBr3 and BCl3, the Bf bond does not break easily because it has a partial double bond character in comparison to BBr3 and BCl3. So what it is going to do is it is going to form an adduct Bf3OH2. So oxygen is going to form a coordinate bond with boron. Just let me show you that. So we have B, we have the water molecule oxygen. So this is going to share its electron pair and form a coordinate bond, and this is going to be Bf3, and here we are having water. Okay, so there is going to be a coordinate bond formed between Bf3 and water. This is going to form a complex, and hence it is not going to get hydrolyzed. In comparison, BCl3 and Bf3, they get hydrolyzed, the bond gets broken, and what is formed? It is boric acid that is formed, and along with it, if it is going to be BCl3, HCl will be formed, and BBr3, it is going to be HBr that is formed. So in case of boron trifluoride, it does not undergo hydrolysis because the Bf bond is very strong due to extensive P by back bonding. Alright. So this is again something that you have to remember. All these questions which I am telling you as application, they are coming as actually questions in the examination, and we have put them all together for you so that none of these you may do them wrong. So next let us discuss Bf3 versus Bf4 negative. So in Bf4 negative, boron is going to form 4 sigma bonds with the fluorine atoms, whereas in Bf3 it is 3 sigma bonds. So what about the hybridization of boron in both of them? In boron trifluoride, it is 4 sigma bonds, it means sp3 hybridization, and in boron trifluoride, it is going to be sp2 hybridization. So now this is all sigma bonds. There is going to be no partial double bond character. Hence what we see is that the bond length of the Bf bond, this is going to be longer in Bf4 negative in comparison to the bond length of Bf3. Alright. So the bond length of Bf bond is shorter in Bf3 in comparison to Bf4 negative. Why? This is because in Bf3 there is back bonding, whereas in Bf4 negative there is no back bonding. There is no available vacant orbital for boron now to undergo back bonding. Alright, and the dipole moment similarly of the Bf bond is going to be more in Bf4 negative as compared to boron trifluoride, because here it is only sigma bond. The lone pair, this is not being shared with boron. So the electron pair is going to be more towards fluorine, which is more electronegative, and hence we will be having a more dipole moment for the Bf bond in comparison to the Bf bond in Bf3. Alright, I hope this is all clear. Great. So let us see one more application of the Bf bond. So many applications you are learning, and all of these applications anyone can come in the exam. These all are very important. So the application that is here we have is that the Bf bond length in Me3N dot Bf3, this is 1.35 Armstrong, which is much longer than the 1.30 Armstrong in Bf3. Again, why? So what is first of all this compound? Well, this compound is formed by the reaction of Bf3 with Tri Methyl Amine. So this is what we have as Tri Methyl Amine. Me is standing for the methyl group. So this is what we have now. Nitrogen has a lone pair of electron. Bf3 is electron deficient. You all know that very well, right? So boron has only 6 electrons. So Bf3, this is going to act as a lowest acid, and trimethylamine, this is going to act as a lowest base. It is going to share its electron pair with boron, and the octet of boron is going to get complete. Now what is going to be the hybridization of boron? It is forming 4 sigma bonds. So it is going to be again sp3 hybridization. So all these Bf bonds now they are going to be sigma bonds. There is not going to be a partial double bond character because the octet of boron is already complete. So what does that mean? It is just being similar to the Bf4 negative case that we have over here. So back bonding in Bf3, this imparts double bond characteristics. That is why the bond length in Bf3, this is going to be 1.30 Armstrong, whereas in Me3N dot Bf3, Bf3 is forming an adduct. The back bonding is no longer going to be present, hence the double bond characteristic this disappears, and hence the bond this becomes a bit longer than earlier. It is going to be 1.35 Armstrong now. Okay, again, I hope this is clear. Let us see now one more question as far as Bf3 is concerned, and then we will be moving on to the next molecule. So the last one of the Bf bond, this is a question for you. The Bf bond, this is the strongest in which among the following? Bf4 negative, H3N Bf3, Bf3, H2N Bf2, or HBF2. So I would like you all to pause the lecture over here and try finding out the correct answer yourself, and then look at the solution. This will increase your knowledge further. So now if you've done it, let us look at the solution. First of all, what do we have? We have the Bf4 negative ion. Alright, so in Bf4 negative, what you all know is that boron is making 4 single covalent bonds. Boron is going to be sp3 hybridized, and boron will not be having any empty orbital to participate in back bonding with fluorine. So there is going to be no back bonding. Next we move on to H3 and Bf3. So here again what you can see is boron is making 3 single bonds with fluorine, and one is a coordinate bond between nitrogen and fluorine. So sp3 hybridization again for boron, the octet is complete. There is no empty orbital for boron to participate in back bonding. So again there is going to be no back bonding for this complex as well. Next we move on to Bf3. So Bf3, you all know that boron is having an empty orbital and fluorine is having electron pair to donate. Fluorine is second period element, boron is a second period element, so both of them they can participate in back bonding and hence they do. And what do we have is that the contribution by each fluorine atom to forming the double bond is going to be 33%. All of them they are contributing equally, right? So for each BF bond, the percentage partial double bond character is going to be 33%. Now let us look at the next molecule. The next molecule is H2NBF2. Now here we have again boron forming 3 bonds, 3 single covalent bonds, that is with 2 fluorines and 1 with nitrogen. Okay, so again it is sp2 hybridized. The octet of boron is not complete. It is having an empty orbital in which it can accept an electron pair. And the electron pair, now this can be provided by the 2 fluorines also and by the nitrogen also. And you all know that nitrogen, this has lower electronegativity than fluorine. So nitrogen, this will be having a better donor tendency in comparison to fluorine. Fluorine will have a tendency to pull the electron pair more towards itself in comparison to nitrogen. So the partial double bond character to the boron nitrogen bond that is going to be imparted by nitrogen is going to be more, and the partial double bond character now of the BF bond, this will be less than 33%. I hope you can understand this. So it is going to be less than 33% partial double bond character for each of the BF bond. And now let us look at HbF2. So in HbF2, what you can see is again boron is making 3 bonds, right? So again the octet is not complete. It is having empty orbital, and fluorine can contribute a electron pair to the boron so that its octet get complete and hence the back bond is possible. But now we have 2 fluorines which can participate in back bonding. So it is going to be 50% character of both the fluorines in formation of the double bond or the pi bond. So out of all these, well, Bf4 there was a single bond. In here also it is a single Bf bond. Here we have 33% double bond character of the Bf bond. Here it is going to be less than 33% character, and here it is 50% character. And stronger is going to be the partial double bond character of the Bf bond. It is going to be the strongest. So the correct option is going to be HbF2. So I hope you have increased your learning today with lots many questions. There are so many more coming up. Let us continue. So let us look at now the next molecule that is going to show back bonding, and that is going to be Bf3. Again, the donor over here is going to be the fluorine atom. And does this molecule exhibit back bonding? First of all, let us remember the conditions. First condition was that we should have a second period element and the other to be a second or a third period element. So fluorine is a second period element and phosphorus, this is a third period element. Apart from that, what do we need? We need one of the atoms to be having a lone pair of electron and other to be having empty orbitals. So let us look at the configuration of fluorine and phosphorus quickly, because you know that all. So phosphorus, this is going to be outer shell configuration 3s2 3p3, and after that, well, we have 3d orbitals which are going to be empty. And as far as fluorine is concerned, it is going to be 2s2 2px2 2py2 2pz1. So it has lone pair of electrons in the p orbitals. So it satisfies all the conditions which are required for back bonding. So let us see back bonding in Bf3. So here what you are going to see is that phosphorus is going to form 3 bonds with the fluorine atoms. It is going to have its lone pair of electrons also. Here the octet is going to get complete for the Bf3 molecule. It is not that the phosphorus octet is not going to be complete, but still this exhibits back bonding with fluorine because it has vacant d orbitals. Alright, so fluorine is going to participate in back bonding by being the donor. It is going to be the lowest base, and phosphorus is going to be the lowest acid by accepting that lone pair of electron. The nature of the back bonding, this is going to be a 2p pi, a 3d pi back bonding. 2p pi for fluorine and 3d pi for the phosphorus atom. Always write first of all the atom which is contributing the lone pair and the other which is receiving after that. Alright, so 2p pi, 3d pi back bonding, and well then after this again we have 3pf bonds, so all of them they can contribute to back bonding. So we will be having 3 resonating structures, and this is going to be the resonating hybrid. So all of the 3pf bonds they are going to have a partial double bond character. And because a partial double bond character is developing in all the bonds, so there is going to be a shortening of the bond length. We see that the bond length, this is 156 picometer, and the bond angle, this is 96.3 degrees Celsius. What is the significance of this angle? Also, I'm just going to talk about the application of this as well. So let us talk about now the applications which we have to learn regarding the PF3 molecule. So let us now compare PF3 and the PH3 molecules as a first application of this back bonding concept in PF3. So here what you find in PF3, as you know, is that there we have a 2p pi, 3d pi back bonding in case of the PF3 molecule, which imparts a partial double bond character in all bonds. Thus there is going to be a shortening of the bond length, whereas in PH3 back bonding is not going to take place, so there is going to be no shortening of the bond length. The next very importantly what you have to remember is the difference in the bond angles of PF3 and PH3. What we find is in PF3 the bond angle is 96.3 degree, whereas in PH3 the bond angle is 93.5 degree, which is less than that of PF3. Now, why is very important? Well, you will have to understand that with the understanding of the bond angles is NH3 and NF3. Alright. So you have already studied the concept that when we have a central atom to be the same and the surrounding atoms they are different, then what is going to be affecting the bond angle? The electronegativity of the surrounding atom. So here in the case of NF3 and NH3, you all know that fluorine is going to be more electronegative than nitrogen, right? And then what is going to happen? Well, fluorine is going to pull the electron pair towards itself. So that is going to result as a decreased electron density on nitrogen. And when there is going to be a decreased electron density, well, these bond pair of electrons, they can afford to come closer. So as a result, what we find is that in NH3, this bond angle, this is 107 degrees, whereas in NF3, the bond angle is 102 degrees. So if we just go by the same trend, PF3 has the same central atom as PH3. Fluorine is going to be more electronegative than hydrogen. So fluorine is going to pull the electron pair toward itself. The electron density on phosphorus should decrease, and the bond angle for PF3 should be less than that of PH3. But what we find is contradictory to that. What we find is in PF3 the bond angle, this is larger than that of PH3, and now you know why. That is because of back bonding. Fluorine has donated its electron pair to be shared with phosphorus, so there is going to be an increased gain electron density on phosphorus, and therefore there is going to be more repulsion between the bonded pair of electrons, and the angles they are going to increase. So in PF3 and PH3, the variation of the bond angles, you can now understand this is because of back bonding, whereas in NH3 And NF3 comparison, there is going to be no back bonding in NF3. Alright, and why is there no back bonding in NF3? Because fluorine has a lone pair of electrons, but nitrogen does not have empty orbitals, whereas phosphorus, this has vacant d orbitals. Okay. So now that you know that Bf3 and Pf3, both of them, they show back bonding, let us compare the Bf bonds in both of them. So what we have is that the extent of back bonding in case of Bf3, this is going to be more than that of Pf3, because in case of Bf3, it is going to be a 2p pi 2p pi overlap, whereas in case of the Pf bond, it is going to be a 2p pi 3d pi overlap. So what are we going to have? This is going to be of similar size that the orbitals, they are overlapping, whereas in case of PF3 it is going to be a difference in size as the effective overlap is not going to take place as we have in case of PF3, right? So we will be having back bonding to be better in BF3 and we have in PF. The next what we have is the partial double bond character, which we will be seeing that in both BF3 and PF3 there is going to be imparted a partial double bond character, but we can say that it is going to be a better one in case of PF3 as compared to PF3, again because of a better back bonding in case of PF3. Next we talk about the bond angles. So here there is going to be no change in the bond angles in BF3 because there is no lone pair of electrons, whereas in the case of the PF3 molecule there is a lone pair of electrons. So what we will be having is that there will be change in bond angles as well, as you have seen earlier. So just what you have to remember here is that BF3, this has a stronger partial double bond character, and consequently this is going to behave as a less electron deficient molecule in comparison to PF3. So now let us move on to the next donor atom, that is oxygen, back bonding with oxygen as the donor atom, and the first molecule that we will be studying here is Cl2O. Alright. So here first of all, let's looking at the molecule. Can you tell whether back bonding is going to take place or not? Well, oxygen, this has a lone pair of electrons. Chlorine, this has empty d orbitals. Oxygen is a second period element. Chlorine is a third period element. So the necessary conditions, yes, they are being satisfied by the molecule. So let us see how the back bonding is going to take place. First of all, we have the electronic configuration of chlorine, where you can see that one of the 3p orbitals is half filled and the 3d orbitals, they are empty. Then we have oxygen, which is having two half-filled orbitals. Two half-filled orbitals means that this can form two bonds with one chlorine atom each. So this is going to be two sigma bonds that oxygen will be making with chlorine. And after the formation of the sigma bond, there is still one 2p orbital left, which is fully filled with a lone pair of electrons, and we have the 3d orbitals of chlorine. So here you can just understand that this is a 3d orbital and not a p. It is just to understand this orientation that this has been made this way. Otherwise, you all know what is the shape of the 3d orbitals and what is going to be the shape of the p orbitals. Alright. So what do we have? We have these to be oriented in a similar fashion. So an overlapping can take place between them, and hence we will be having the formation of a pi bond between oxygen and chlorine. It is going to be what? It is going to be a 2p 3d pi back bonding. Alright. And now this can be between one oxygen and the chlorine, or it can be between the chlorine and the other oxygen. So these are going to be the two resonant hybrids and the resonating structures, and this is going to be the resonating hybrid for the molecule. Alright, now in this molecule what you can see is that oxygen is having a partial positive charge and chlorine, this is having a partial negative charge. Actually what is going to should have happened is that the electronegativity of oxygen is more than that of chlorine. So oxygen should be having a partial negative charge, but it is because of back bonding that oxygen is donating its one lone pair of electrons, and hence it is having a partial positive charge, as you can see in the diagram. Okay. Now the lone pair of the oxygen and the vacant d orbital, this is making a 2p pi 3d pi back bond, so that you all know. And now the another thing is that now the oxygen has utilized one of its lone pair in the bond formation, so the lone pair repulsions, they are going to decrease, and hence the bonds, they can afford to spread. All right, so what do we see? We see that the bond angle, this is going to increase than the expected value of 109.5 degrees. I hope you can understand that oxygen, this has two lone pair of electrons and it is forming two sigma bonds. So the hybridization of the oxygen atom over here, it should be sp3 hybridization. And for sp3 hybridization, if it is all single bonds, the bond angle should have been 109.5 degree. But because of the lone pairs, what we say is that the repulsion increases and the bond angle value decreases. But now this is because of back bonding. What has happened to the hybridization of oxygen? Now it has just one lone pair of electrons. It has utilized the other lone pair of electrons in forming the back bond, and it is also forming two sigma bonds. So two sigma bonds plus one lone pair of electron, it is going to be sp2 hybridization, not sp3. So here the hybridization of the oxygen molecule, this has also changed. So that is very important for you to remember. So the hybridization is sp2 now, not sp3. Okay, and the bond angle, what you can see is now that it is changed to 110.8 degree. For sp2 hybridization, what is the bond angle? It is going to be 120 degree. But now we have one lone pair of electrons, and you can say that they are going to be two sigma bonds. So lone pair bond pair repulsion is more and the bond pair repulsion is less. So the bond angles, they come closer to one another in comparison to the 120 degree angle. Okay, and if we look at 109.5 degrees, and that is what we are looking at the sp3 hybridization, which should have been there in the molecule, but because we had to explain the value of this angle, well, we had to introduce the concept of back bonding. So I hope now you have all the feel that you should be having, and now we can do quickly the rest of the things as well. So next, let us look at an application of this molecule as well. We have the bond angles to be arranged in the increasing or decreasing order in the following molecules: OF2, H2O and OCl2. So looking at the molecules, if you did not know the concept of back bonding, what would have you thought? You would have thought, well, we have all the molecules having oxygen to be the central atom. It is making two sigma bonds with fluorine, hydrogen and fluorine, and it is going to have two lone pair of electrons, right? So two bonded pair of electrons, two lone pair of electrons. The hybridization of oxygen is going to be sp3, and because it is two lone pairs, so it is going to be a deviation from 109.5 degree angle, and this deviation, this is going to depend upon the electronegativity of the surrounding atom, and more is going to be the electronegativity value of the surrounding atom, smaller is going to be the bond angle for the molecule. Why? You all know, you have just now studied it in the case of the NF3, that it is going to pull the electron pair towards itself if it is going to be more electronegative than the surrounding, the central atom, right? So if the central atom, now this is going to have less electron density, the bonded pair of electrons, they are going to feel less repulsion and they will come closer to one another. So what this means is that the expected bond angle order, this is going to be OH2, OCl2, OF2, because fluorine is the most electronegative, then chlorine, and then hydrogen, right? So it is going to have the maximum pull of the electron pair towards itself and least electron density on oxygen, right? I hope this is clear now. But we know that OCl2, this is going to exhibit back bonding because it is having oxygen to be have a second period element having lone pair of electrons, and chlorine being a third period element, it is having a 3d vacant orbital. So here they can undergo back bonding, which is going to be a 2p pi, a 3d pi back bonding. And when this is going to happen, what is going to be there? There's going to be a partial pi bond a partial double bond character imparted to both of the bonds, the OCl bonds. And you all know that if there is an increase in bond multiplicity, well, it is going to be an increased electron density on the central atom. There is going to be an increased bond pair repulsion now, right? And therefore it is going to be more repulsion, so this is going to open up the bond angle in case of OCl2. And what do we find? We find that this angle is going to be now 110.8 degrees. Okay. Another thing which is going to play a role over here is that oxygen, initially it had two lone pair of electrons, but now one of the lone pair of electrons of oxygen, this is going to be involved in the bond formation. So the lone pair repulsion, that is also going to decrease, and hence the bonded pair of electrons, they can open up. So because of these two factors, what are we going to see? That the bond angle in case of OCl2, this is going to increase. And therefore, what is going to be the bond order? Well, the bond order is going to be OCl2, OH2O and OF2 being the least. Okay. So I hope this is clear. This is an important question, very frequently asked in the examinations. Let us look at one more application of the OCl2 back bonding. We have OCl2 bond angle to be 110.8 degrees, whereas SCl2, this has a bond angle of 102 degrees, and you have to explain why. So in OCl2, the bond angle is larger because of the back bonding in the molecule. So you all know now why. Alright. And SCl2, well, SCl2, there is going to be a bond between sulfur and chlorine. First of all, the necessity conditions, if you remember, one of them, it has to be a second period element. Both of them, they are third period elements. So they are not going to undergo back bonding. Alright. And the lone pair of electrons on both sulfur and chlorine, they do not delocalize owing to the availability of the vacant d orbitals on their own. So there is going to be no back bonding in case of SCl2. So it is going to be the normal concepts of chemical bonding that we have the bond angle to be 102 degrees. Sulfur is going to be the central atom, chlorine is going to be more electronegative, it is going to pull the electron pair towards itself. Sulfur will be having a decreased electron density, hence the bonded pair of electrons, they can come closer to one another. Right, so I hope this is clear. Now the next one, let us look at one more. We have the bond length of the BO bond in BOH3, that is boric acid, to be less than the bond length of BO bond in BOH4 negative. So here again, just looking at the molecules or the ion, can you tell which of them is going to undergo back bonding? We are going to have a back bond between boron and oxygen in BOH3. This is boric acid formula. So here we will be having a back bond formed between boron and oxygen. Oxygen is going to have the lone pair of electrons. Boron, this has an empty orbital, so back bonding is possible. Both of them, they are second period elements. Whereas in BOH4 negative, boron is going to make 4 sigma bonds, and hence it is not going to have a vacant orbital. Alright. So due to the back bonding of oxygen atom with boron in BOH3, the bond is going to adopt a double bond character, and there is going to be a shortening of the BO bond length. The back bonding does not occur in BOH4 negative. Alright, so I hope this is clear. Now these things should be very easy for you to understand. Just look at the molecule and you should be able to tell whether it is going to have back bonding or not. And if it is going to be a back bonding, you know now what are the effects of that. So now let us look at the next one very quickly, because you have an understanding of the concept now, right? So we have SiH3 twice oxygen. This is going to be what? It is going to be diacylyl ether or disiloxane. So here what you can see is that oxygen is going to be the central atom. It is going to form sigma bond with 2 silicon atoms of SiH3 silyl group. Alright, so what you can see, oxygen, it is forming 2 sigma bonds. It has 2 half-filled orbitals. Silicon, this is forming 4 bonds. It is forming 3 bonds with hydrogen and 1 with oxygen. So again, it has to be in its excited state so that there are 4 half-filled orbitals, right? So again, can this molecule show back bonding? Because it has oxygen to be a second period element, silicon to be a third period element, what you can see is that oxygen, it is going to have a lone pair of electrons. Silicon is having empty d orbital 3d orbitals, so yes, they can show back bonding, right? And when there is going to be back bonding, what are going to be the effects? What you're going to see is that there is going to be a partial double bond character for both of these, right? So we will be having a resonance hybrid, and what you can see is that the bond length of the SiO bond, this is going to be less because of the strong bond. And if we are going to compare it now to a CO bond, which we will be doing in the next. So let us see an application of this molecule as well. We have dimethyl ether comparison with diacylyl ether. Dimethyl ether CH32O, diacylyl ether SiH32O. Alright. So if I draw the structures for both of them, it is going to be oxygen SiH3 and SiH3, and for dimethyl ether it is going to be oxygen with CH3 forming a bond with carbon, and here also forming a bond with carbon. So oxygen is common to both of them, and here we have a second period element, here we have a third period element. Both are forming 4 bonds. After that, silicon will be having vacant d orbitals, carbon will not be having vacant d orbitals, right? So here what we are going to see is that dimethyl ether, there is going to be no back bonding occurring, whereas in SiH3 to oxygen diacylyl ether there will be back bonding. And because there is back bonding, so the lone pair of oxygen that is going to be utilized for the back bonding, whereas here it will not be utilized. Hence oxygen is going to use that lone pair of electrons to donate to Bf3 and form a complex with it. Here this is not possible, right? I hope this is clear. Let us look at one more application. There is a huge increase of bond angle in diacylyl ether in comparison to bimethyl ether Y. So what you can see is that oxygen, both of them, if it is going to be 2 lone pair of electrons, if you compare it with the water molecule, this has a bond angle of 104.5 degrees. If you compare this with the bond angles in both these molecules, what you will be finding is that in diacylyl ether, the bond angle is 144 degrees. Dimethyl ether, the bond angle is 110.8 degrees. Why is it so? In dimethyl ether, the bond angle, this increases in comparison to if you do that with the water molecule, where also oxygen will be having 2 lone pair of electrons. It is an increase because of the steric hindrance of the large methyl groups. Okay, so they are going to be large methyl groups, they are going to repel each other, and the bond angle is going to increase. In case of diacylyl ether, again we have large groups which are attached to oxygen, so there is going to be steric repulsion. But here the problem is that you are seeing that this is a big increase. Why is that a big increase? Well, that is because of back bonding. So back bonding from oxygen to silicon, and partly during steric hindrance, what we see is that there is a large bond angle in case of diacylyl. Okay, I hope this is clear. So one more comparison over here of diacylyl ether with Cl2O. Now the bond angles with both of them, again a huge difference. Here it is 144 degrees and Cl2 it is 110.8 degrees. Why? Why are we comparing them? First of all, both of them, they show back bonding. Both of them show same type of back bonding. It is going to be a 2p pi, 3d pi back bonding. But again, why a large difference of the angles? Well, this is attributed to 3 lone pair of electrons on each chlorine atom in Cl2O, which are going to retard the flow of electrons from oxygen atom to chlorine in Cl2O, whereas in case of diacylyl ether, silicon will not be having those lone pair of electrons, hence there is a free flow of electrons. So it is going to be a better back bonding in diacylyl ether as compared to Cl2O. Now let us see one more example where we have oxygen as the donor atom. It is going to be the boroxine radical, that is B3O6 negative, or you can say it is going to be the oxygen as the donor atom for back bonding in H3B3O6, that is metaboric acid. Okay, so what you will be seeing over here is this is going to be the structure. We have a ring like structure. This is a benzene like structure. The ring is planar and it is going to be aromatic. Again, what you can see is that each boron atom, this is making 3 sigma bonds. 3 sigma bonds means it is going to be electron deficient. It is going to be having an empty orbital, and it is going to be a second period element. Oxygen is a second period element. It has lone pair of electrons. So here back bonding is possible between boron and oxygen. And when this back bonding occurs over here, what we find is that this is a complete full coordinate pi bond which is formed as a resonating structure. It is not partial double bond character, it is a complete double bond which is formed between boron and oxygen. So again, this is going to be one resonating structure, this is going to be the second resonating structure, and we will be having a resonating hybrid where it is going to be that these 3 pi bonds of the ring, they will be delocalized over the whole molecule. So this is just similar to the benzene ring that we have. Alright, and that is attributed to the back bonding between oxygen and boron. Similarly, this is one more example that we have of borazine, that is B3N3H6, which is having a back bond between boron and nitrogen. So this is something that we are going to discuss in the next lecture, where we will be talking about back bonding with nitrogen as a donor atom. But because both of these structures, they are similar, so I thought why not just put them together so that you remember this. So borazine B3N3H6, this is in fact called as inorganic benzene because it has a structure similar to that of benzene. Alright, and that is attributed again to the back bonding between boron and nitrogen. Nitrogen is going to be the electron pair donor and boron is going to be the electron pair receiver. Okay. So now let us look at one more property being affected by back bonding. We have R3SiOH being more acidic than R3COH. So one way at looking at a substance which is going to be more acidic or not is to see whether its conjugate base is going to be more stable or not. So when we see R3SiOH, the back bonding from the lone pair of oxygen atom to silicon, this increases the polarity of the OH bond and this stabilizes the conjugate base R3SiO negative. Alright, so it is going to be a stabilization of this conjugate base of this acid by a back bond which is formed between silicon and oxygen, whereas this is not going to happen in the case of R3CO negative. That is not going to be stabilized because there is going to be no back bonding between carbon and oxygen because of the absence of the vacant orbitals for carbon, right? So for this we will be finding that R3SiOH, this is more acidic than R3COH. And for similar reasons, we can also say that the bond order of SiOH, this is going to be greater than COH. Alright, the next one we have R3NO. This has a higher dipole moment as compared to R3PO. So what you see is that the dipole moment value for R3NO, the NO bond, this is 5 dBi, whereas for the R3PO, it is 4.37 dBi. Actually, what should have happened is that phosphorus and oxygen, if you compare the electronegativity difference, that is going to be much more than the electronegativity difference between oxygen and nitrogen. So this should have a more dipole moment as compared to R3NO. But because there is back bonding occurring between phosphorus and oxygen, what do we see is that there is going to be electron density shift from oxygen to phosphorus. So there is less of an electronegativity difference between the two, phosphorus and oxygen, and hence we see a lower value of the dipole moment. So before we conclude this lecture, well, there are going to be just two examples that I will be discussing more with you. And the first one you can already see, that is carbon monoxide molecule. This shows back bonding, right? Now, when we started learning chemical bonding, we are on to the 39th lecture, and we learned first of all the lowest structures for these molecules. And when we were learning the lowest structures, what we studied was that carbon, this has 4 valence electrons, and oxygen, this has 6 valence electrons. Both of them, they are going to put 2 each in the center, and this is going to be the formation of a double bond between them. All right, and then what is going to happen? Well, what is going to happen is that oxygen's octet is going to get complete with two lone pair of electrons and a double bond between both of them, but carbon's octet, this does not get complete. So then what did we learn further? What we learned further is that between carbon and oxygen, a coordinate bond is possible. Oxygen atom, this is going to share its lone pair of electrons with carbon. Fine. So after that, what did we learn? We learned about sigma bonds, we learned about pi bonds, and we learned that the first bond between two atoms is always a sigma bond. The second bond and the third bond, this is a pi bond. So here we have first of all a sigma bond between carbon and oxygen. Then it is going to be a pi bond between carbon and oxygen, and both these sigma and one pi, well, they are formed by the equal sharing of electrons by the two atoms. But then the third bond, which is formed as a coordinate bond between carbon and oxygen, this is also a pi bond. So carbon and oxygen, they are forming a coordinate pi bond now, and you have learned now that back bond, this is a type of coordinate pi bond. Carbon and oxygen, both of them, they are second period elements. One has an electron pair which it can share. So it is going to act as a lowest base, and carbon, well, which is having one empty orbital. So it is going to accept that in that empty orbital. So it is going to act as a lowest acid. Okay. So this is going to be a summarization of the whole of chemical bonding actually that you have learned from the start to almost the end of chemical bonding with this lecture. Alright. So carbon monoxide molecule, this shows back bonding. The third bond between carbon and oxygen is a coordinate pi bond. Now the last one with which we are going to conclude this lecture, the rest we will be continuing further in the next, that I've also already told you that nitrogen, carbon and other halogen atoms as donor atoms are still left that we have to discuss. So that we will be putting up another lecture. It's almost quite a long time that we have been studying. But I think this was an interesting lecture because we have studied so many examples today, and all of them, they are very important, coming frequently in the examination. Alright, so the last one, well, the most interesting one of the whole lecture. What you can see is this a big name, so I would prefer showing you the structure of this molecule that we have. So here what you can see is that we have oxygen in the center. It is forming two sigma bonds with two aluminium atoms, and the two aluminium atoms, they are further forming two sigma bonds with the CF3 groups. So each aluminium atom, this is forming three bonds. When it is forming three bonds, one of its 3p orbital, this is going to be empty, and this is a third period element. Oxygen is forming two bonds. It is a second period element. It has two lone pair of electrons. So both of the atoms, when they satisfy the conditions for back bonding, and back bonding does take place over here between oxygen and aluminium. So what is interesting about this example that I'm telling you? Well, the interesting thing over here is, in all these examples of oxygen as the donor atom, what you have seen is that only one of these two lone pair of electrons, this participates in back bonding. Whereas in this molecule, well, both of the lone pair of electrons, they are going to participate in back bonding. One of the lone pairs, where this is going to form a back bond with aluminium on one side, and the other one is going to form a back bond with aluminium on the other side. So this is special because this is forming two back bonds. Till now, we had never seen an example where there were two back bonds. So why is it so again now? Well, this is because now we have a group, that is CF3 group, attached to aluminium. And in the CF3 group, what do you have? You have three fluorine atoms. And fluorine, you all know, they are the most electronegative element of the periodic table. So what are they going to do? Well, they are going to pull electrons from carbon towards themselves. Okay. So carbon, well, in the return, this is going to do what? This is going to ask aluminium to give me more electrons because fluorine is pulling more electrons from me. Please help me out. And this aluminium, poor fellow, this is already electron deficient. Fine. So what is it going to do? Well, it is going to request oxygen, please give me electrons. You have a lone pair of electrons. So the CF3 group, well, this acts as a electron withdrawing group, a highly electron withdrawing group, and by the inductive effect, which you will be learning more in actually organic chemistry, do not worry, but this much at least you can understand that fluorine is going to pull the electrons from carbon, carbon is going to pull the electrons from aluminium, and aluminium is going to ask oxygen, please help me. So oxygen does help this poor fellow aluminium, and hence there is a back bond formed between oxygen and aluminium on both sides. Now, when on both sides oxygen is forming, you can understand that what is going to happen. There are two sigma bonds that oxygen is forming, and it is forming two pi bonds also. So, what is going to be the hybridization of this oxygen? Well, it is going to be sp hybridization now. And sp hybridization, you know that what is going to be the bond angle? It is going to be 180 degrees. So because this is going to be a partial double bond character which is being exhibited by oxygen, so we can say the angle is not going to be exactly 180 degree, but it is going to be almost 180 degree. So wasn't this an interesting example? We have two back bonds being formed by oxygen as a special case in this molecule because of the extreme withdrawing effect of the CF3 group. And for similar reasons, you will be learning more in organic chemistry again, that we have SiO-Si angle in pH3 SiO-Si pH3 to be almost 180 degree, because this phenyl groups which are going to be attached to silicon, again they are going to be electron withdrawing because of their resonating effect. So this is something that I will not be discussing more over here. We will be discussing this when we talk about organic chemistry in detail. So I hope you have enjoyed this lecture with me. You have learned many concepts, you have learned many examples of backbonding, you have learned many applications of backbonding, and this is going to continue in the next lecture. So see you again for that. If you have not subscribed to the channel till now, please do that, because that would not be a lecture you would like to miss. Also, well, if you're liking the lecture, please do give it a thumbs up and do share it with your friends so that they can also gain from the lecture if you are gaining also. So thank you and have a nice day. God bless you.